Well, hey, maybe we can do that here. Too. Absolutely, I'm going to. So yeah, we're going to post this too. Let's see. Quick, can you all hear us out there in Zoom land? Anyone? Just put in the chat. Give me a thumbs up. Okay, thanks, Ash. Nice, that's working. Yes, a couple minutes here. I think we're good to go. Are you? Did you want a winner or? Yeah, that'll work. Yeah. And so yeah, let me get you a picture. This is a point.
At this point, I've been in this research process as long as I've been doing my grad proof. So
Yeah. Oh, so you want to come out here?
I've also given 6 presentations. Just like copy of it.
All right. I'll make sure to send it to you. And you'll probably see me standing up and going and taking some more in the back.
This one is fine.
Okay. Yeah, that works. Okay. Oh, that I think.
Yeah, this one is a
Oh, that's.
anyhow, I use the
That way?
spot race.
Oh, yeah, there you go. There we go. Okay. So yeah, yes, we've got just a couple minutes before we get started. And yeah, like you said, afterwards I'm gonna head out.
I know she's going to be able to quantum sensing. I think that's the.
We have, and like I said, you'll be meeting with Stephanie Hirsch. That's part of this project. We can talk a lot about it. And Sally as well, but yeah, we're gonna have to have follow up on, yeah, definitely, so that's up. And like I said, I've got this, it's not the university. I think we gotta do it. Mhm.
Like face. Alright.
I was gonna be like, yeah. I won't sneak out, like,
I'm like, yeah, you could go again after.
all right, you gotta show something more. I know.
I do see when shit's coming back, so I can take care of the dog, but.
Everything can't be up.
Yeah, but it's about in mid, I can't.
I mean, luckily my time is very straightforward.
How was your?
You know,
I think there's like a mic that kind of
Actually weren't very well on the radio.
see, I was stressed that I couldn't watch it, because someone had to get married.
travel.
Oh, it's 3.5 hours drive
Is it?
from Point. I live in Anderson, so I use this iPhone. So I'm familiar with whenever we visit
No,
Phoenix.
this
we got
terrible guy, I remember.
location.
Yeah, you go like some speak. I didn't get to speak.
Oh, okay.
No, I told, I mean, my brother the best with everyone.
So
I told him, I told Jim. I'm not-
Yeah, we-
Yeah.
It's a
And my brother seems to be,
so we-
he asked me his best, I'm not gonna be
speaker.
Yeah,
Yeah, it's kind of like an every other sort of thing. But yeah.
My brother's gonna be, alright, this man gave me 25 years of pain and suffering, so this speech is gonna be 25 minutes long. And a minute each year pains caused pain, and it'd be 25 minutes.
It's just another minute.
Sounds good.
We're just at 9:45.
Would you like me to give you like 5 minutes, 10 minutes left or anything like that?
I think I have like, I can invest in. Based on the screen. Okay, sometimes I go fast. So I think I'm happy to accept Q&A. Sounds good. I think that's more than we can, we don't want to put people here.
Yeah.
Yeah, you wanna go ahead?
All right, everyone, we're going to get started. It's my great pleasure to welcome our speaker today, Dr. Tiagarajan Soundapan. Sorry if I kind of. But anyways, Dr. Soundapan is currently associate professor at Navajo Technical University and is the head of the chemistry department over there. His research spans several fields, including electrochemical sensors, biosensors, flexible point of care diagnostics, and wearable devices. And also electrochemical energy storage. He received his PhD in engineering, specializing in electrochemistry in 2009 from National Taipei University of Technology. After receiving his PhD, he pursued and obtained several different postdoctoral positions, starting at National Taipei University, then moving to University of Texas at Austin, and then ending the postdoctoral era at Washington University at St. Louis. And that was in 2015. We all have the pleasure of listening to Dr. Soundapan talk about some of his current research, which involves bringing low-cost and portable sensors to underserved and remote areas. So please help me give a warm welcome to Dr. Soundapan.
Thank you. Good morning, all. Thank you, Gabriel, for inviting me to give a research talk at NAU. It's been a pleasure. I cross this location every time whenever I visit Phoenix, but now I got the opportunity to visit NAU and to share our research presentation. Thank you for that. So with all that, I'm going to start my presentation. So empowering future scientists, electrochemical sensor research, and undergraduate training at Navajo Technical University. As I said, my name is Tiagarajan Soundapan. You can call me Soundapan, it's easy to pronounce. My first name is Tiagarajan Soundapan, is my father's name. And most of my students call me Dr. Soundapan, it's easy to pronounce. I'm Associate Professor of Chemistry and also Chemistry Program Coordinator and Head. I'm also a Prem Director at NTU. And this is my email ID, and if you want to contact me, I also embedded a QR code. You can scan it and you can contact me. Before getting into the research presentation, I want to teach some local language called Navajo language. Do we have any Navajo members here? None of us, right? No, okay. So Yate means hello in Navajo language. Okay. So you learned one Navajo language today. And in my presentation, I'm going to give a brief introduction about Navajo Nation and Navajo Technical University and Navajo Nation need and Nest Lab at NTU and Nest Lab student research in electrochemical sensors and energy storage and NTU student success stories and acknowledgements. So who we are, Navajo Nation extended into 4 states, Utah, Arizona, and New Mexico. Diné land, or Navajo land, is largest than 10 out of 50 states in US. And over 400 Navajo young men served as a Navajo code talkers during the World War II. And 68% of the residents speak Diné language, which is Navajo language. And we are located here, Crown Point. And I know the Flagstaff is somewhere here, right? And we have, spread across 3 states. And NTU, we have 35 tribal colleges and universities in US. Out of this 35 tribal colleges and universities, we are unique because we are the only tribal university with both ABET accreditation and Higher Learning Commission accreditation, which means we can teach engineering courses and also science courses. And we also have American Veterinary Medical Association approval, and we also have a culinary arts department. And we are the second institute supported by Navajo Nation. The first one is Diné College, and it's nearby, right? I don't know how far it is from here. Probably an hour.
Yeah, a good hour and a half too.
Yeah, hour and a half. So Diné College and Navajo Technical University is supported by Navajo Nation. And we have high proportion of non-traditional students. So I'm going to show that in the next slide. And this is our main campus. So we started as a vocational center in 1979, and we renamed it as Crown Point Institute of Technology in 2005 with full Higher Learning Commission accreditation. And we became full university in 2013, and we started offering master degree in Diné culture, language, and leadership. And in 2023, we started offering PhD program in Diné studies. And you can see here, this is the aerial view of our campus. And this is the chemistry lab. The annexure is our chemistry lab. This is student union building. And this is our student dormitory. And main campus is located in Crown Point. And we also have 4 satellite campus, 2 in New Mexico. We also support nearby tribal community called Zuni tribe. And we have another campus in Kirtland. We have 2 campuses in Arizona. The main campus is Chinle, satellite campus. This one is bigger, and Tiknaspos. So we also have 2 campuses in Arizona. And I hope this is a Hopi tribe, and we also support Hopi tribe. And as I said, all of our students are non-traditional students, and our students' graduation age is 27. And it's because NTU students are joining NTU with different background, like students with families, students with military background, students from high schools, and all of them are first generation college students. And that's why we have this non-traditional students in NTU. And almost 95% of the students are Native American students. All of them are Navajo students. And we also support nearby tribal community like Hopi, Pueblo, and what else? I forgot the other tribal name. So 3 are, yeah. So 3 or more. So as I said, we started as a vocational center, and we started with certificate programs. Now we have bachelor's, master's, and PhD. And I also started a chemistry program in 2023. And now I have 5 students enrolled, and it's growing. And Crown Point is the main campus. We have a large student capacity in Crown Point. And you come in gender, by gender, we have almost 60% of female students. And this is our enrollment trend since 2018. It got decreased during the COVID pandemic, and it's slowly increasing. So what other things I want to discuss is uranium mining. Do we have any uranium mines nearby here? Yeah. Mm-hmm. So I think Flagstaff is where? It's here. So probably like an hour drive, you may see some uranium mines, right? So Navajo Nation has almost more than 520 abandoned uranium mines. So they just came and they just opened all these mines, and they just left it without closing properly. So our groundwater is completely contaminated, and it is not safe to drink or for human consumption, and also for ranches, it's not safe. So Navajo Nation is severely affected by uranium mining, and because of this, we have a severe health impacts. Most of the Navajo community has this cancer, kidney disease, and other chronic health conditions. And this is a big issue inside the reservation. And we also have 2 abandoned uranium mines nearby the campus. As I said, the abandoned uranium mines are associated with the diseases of inflammation, and almost 4,000 former uranium miners were affected by lung cancer because of uranium mining. And 1 in 5 uranium mines are located within the 6 miles of the reservation. And almost 75% uranium mines are located within 50 miles of the reservation. So if I have students in my class, each student are living nearby some abandoned uranium mine. And this is images are taken in Church Rock. We have a United Nuclear Corporation abandoned uranium mining activity site. And I used to drive this location every day when I lived in Gallup. So still it's there. And you can also see the uranium heap bleaching pond. It's nearby the Puroco River. And people are living in this kind of situation there, and still they don't have any big remedies for the cleanup or anything. I know we have a lot of news, like ongoing news, like EPA is there to clean up, but still we are facing big issues inside the reservation. So this motivated me to train our students in electrochemistry research, and this motivated me to start NEST lab, which is Nano Electrochemical Analysis and Energy Storage Laboratory. So during the COVID pandemic time, Navajo Nation is severely affected, and we don't have any centralized lab facility to diagnose those COVID samples. So we always send the samples to Albuquerque or Phoenix. So we don't have a centralized lab facility, and that is another big issue. So I thought that if I train our students in electrochemistry research, they can fabricate handheld sensors, and we can test those biomolecules or contaminants by themselves. So this is the one motivated me to start this lab. And also, if you look at the second image, still 40% of the reservation, they don't have a direct access to running water facility and also the power grid. So as an electrochemist, I thought that if I train my students in electrochemistry research, they can also learn the energy storage research, and they can start their own startup companies. So I also focused on training them to fabricate lithium-ion batteries, redox flow batteries for energy storage. Because in New Mexico, we have a lot of sunlight, right? We can install solar panels, but we need energy storage. So if I train our students in energy storage sector, they can start their own startup companies. And if you look at the reservation, we don't have any companies inside, right? Even for job opportunities, they have to go to Albuquerque, or they have to go to Farmington or Phoenix. So by training our students in electrochemical sensor and energy storage research, we can go for patents. From there, we can start our own company. And that's how this lab started. And now I have 10 students in this lab. All of them are working under sensors and energy storage. Why electrochemical sensors? How can we compare it with the analytical laboratories? So for blood sample analysis, where do we send our blood samples? You have to stop somewhere, right? At the hospital, TriCore, right? And how long it will take to analyze those blood samples? At least 1 week, right? And you have to pay certain amount of money, like it's going to cost you $300 to $400 for a sample analysis, right? But still, it's a goal. It's a standard one. You have to wait and you have to pay the money. So compared to analytical techniques, handheld electrochemical sensors are promising. So you can connect. This is a handheld potentiostat. You can connect this to your cell phone, and you can connect the electrode, and you can draw the blood, and you can diagnose for glucose or any other cancer biomarkers. Whatever you want, you can do with this handheld device. So that's how I got attracted with electrochemistry, and I learned electrochemistry. And electrochemistry is based on potentiometric and amperometric and voltammetric technique. I'm going to talk about potentiometric technique, but we also have other transducers like electrical, optical, mass sensitive, and thermal. So what is electrochemistry? Does anyone remember the famous proverb taught in Gen Chem 1 or Gen Chem 2 for redox reaction? Oil rig, very good. So what is oil rig?
Oxidation is loss, reduction is gain.
Again, very good. And you know the another proverb, Leo says give, right? Loss of electron is oxidation and gain of electron is reduction. So electrochemical sensors are based on this redox reaction. So either we oxidize the substance on electrode surface or we reduce the substance on electrode surface. And the current is measured and amplified, and we can plot the calibration plot. From there, we can get the detection limit, sensitivity, linear range, and everything. And we use cyclic voltammetry as a standard technique to analyze any samples or electrodeposit films or to study the electrochemical system. We use CV as the standard. We have 15 electrochemical techniques. So here you can see the electron goes from the working electrode and it got reduced and it got oxidized. And this is how we study the system. And we use CV for to study the redox behavior of any system. And this is the base system we use. And we also have other techniques called linear sweep voltammetry, square wave voltammetry, almost 15 electrochemical techniques. But this is the gold standard for to diagnose or to analyze anything. And this is the main components of electrochemical biosensor. So we focus on here the catalyst or the electrode surface where the electrochemical reaction will take place. So this substrate, this target analytes are going to be oxidized or reduced. So and the current is going to be amplified, and it got transduced, and it got amplified, processed, and displayed. And you can see the simple scheme here. So we apply voltage to either oxidize or reduce the substance, and the substrate will become product, and resulting current is magnified, amplified, and we see in the form of digital numbers. And to do this, we adopt a simple electrochemical cell, which consists of working electrode, counter electrode, and reference electrode. And all the reactions will take place at the working electrode surface. And these are all commercially available traditional classic carbon electrodes, platinum electrodes, gold electrodes. And we can use these electrodes to study the electrochemical activities of any substances. And this is a typical 3 electrochemical cell. And using electrochemical biosensors, we can lower the over potential for the redox species, and we can increase the current signal. We can detect multiple species simultaneously and also selectively. So the great advantage of electrochemical sensing is either you want to detect only one species or multiple species, you can do that by optimizing the electrode surface. And it is also helping us to eliminate the interference signals, and we can go to the bottom and we can go to the top, like lower detection and also the higher level detection. And these are all commercially available electrochemical sensors. I believe some of you might have used this one, right? You might have bought this one from Walmart. And this is the base for all the electrochemical sensing. And nowadays we have advanced version. I'm gonna discuss one by one. So where this started, how this electrochemical sensing research started, it started in 1962. Clark and Lyons invented the first commercial blood glucose sensor. They modified electrode with glucose oxidase enzyme, where we can oxidize the glucose into gluconic acid, and we get the hydrogen peroxide. This hydrogen peroxide got oxidized on platinum surface, and we can measure the current, and it can be amplified, and we can match it with the glucose concentration. So that is how it started. Still, the glucose sensor market value is $21 billion. And these are all like, different companies, they fabricate these electrodes. And how many of you use these electrodes? Some of you might be, right? I also use this to check my blood glucose by myself. So it's all started with this blood glucose sensing. But now we are heading into the different direction. And does anyone have a continuous CGM sensor on your arm? No? Okay. So this is the latest one. So for blood glucose, you have to draw the blood and you have to apply the blood on the electrode surface and you have to throw it. But CGM, continuous glucose monitoring, is recently introduced, and this is also based on electrochemical sensing. And Dexcom is the first company introduced this, and Abbott is the second one. And these two sensors can be used for 2 weeks. So you can patch your sensor on your arm, and you can keep tracking on your blood glucose level continuously for 2 weeks. So type 2 diabetes, I believe most of us have type 2 diabetes, not here, I believe. But if you have type 1 diabetes, you have to keep monitoring your blood glucose continuously. So for those people, this is the best sensor. And for type 2 also, we can use it. And now we have a latest one from Sensionics. This sensor can be used for 365 days. I don't know about the reliability of the sensor, but you can patch it and you can keep it for almost 365 days, almost a year. So for all these sensors, you have to fabricate electrodes, right? And that's what we do at Nest Lab. So we fabricate, so these electrodes are fabricated at Nest Lab. So we fabricate these electrodes in Nest Lab, and we deploy these electrodes to detect chemicals and biomolecules, heavy metals, and also cancer biomarkers. And through this research, we are also targeting to start some startup companies inside the reservation. And we mostly focus on materials research and electrocatalytic application. And I really want to start the research in low-cost sensing. So our paper electrodes are less than 2 cents, and it's easy to fabricate. So that's how we built this lab. And all of my students are undergrad students, so I want them to start something simple. And also I want to integrate this with healthcare system so that, we can sell these electrodes to the public. So this one is fabricated at Nest Lab. And what target analytes we decided to do is a detection of ascorbic acid. Nowadays, we don't have scurvy disease. We consume enough vitamin C, right? And on those periods, we have scurvy disease. But still, this is an essential biomolecule in blood. If you want to detect dopamine or uric acid, this is going to be an interfering compound. So we started with this 3 simple. And dopamine deficiency will end in Parkinson's disease. And we also developed a sensor to detect dopamine. And uric acid, excess levels of uric acid will result in gout and hyperuricemia. And our paper electrodes are capable of detecting uric acid also. So these 3 biomolecules we targeted first. And we also targeted endocrine disruptors, which is called as bisphenol compounds. How many of you have a water bottle with you? So how do you buy a water bottle? Do you, except price, are you going to look for any other things? So you have to make sure that your water bottle is BPA free, right? How many of you checked that? None of you, right? So nowadays we have BPA free water bottle, but like 5 years back or 7 years back, most of the plastic water bottles are made up of BP compounds. And if you got exposed to BP, it will end in type 2 diabetes. So not only water bottles, baby feeding bottles, pacifiers, all these materials are made up of plastics, and long-term exposure of BP compounds will end in type 2 diabetes. So we also decided to develop a sensor to detect bisphenol compounds. And not only water bottles, I believe all of us are using canned foods, right? And that canned food has liners, also those liners also made up of BP compounds. And aerosol cans and beverage cans. I think beverage cans, it's okay, it's made up of aluminum, but some beverage cans still there, and coffee cans. So these cans has the BP liners. If you got exposed to this BP compound, you will end in type 2 diabetes. So we decided to detect these BP compounds using our paper electrodes. So we started with bisphenol A, which is restricted in many countries now, but this is the one used in food containers, bottles, coatings, and also in medical devices. And this is a strong endocrine disruptor. And we also have BPB, bisphenol B. The structure is shown here. And this is used in specialty plastics. And this is also a strong endocrine disruptor. And we don't have any restrictions, still we don't have any strong restrictions on BPB. And BPS, this is commonly used as a substitute for BPA-free products, but still this is considered as endocrine disruptor, and we have to detect and keep monitoring these three compounds. The first one is phased out almost, but still we have two more, and still we are using this to make those plastics. So in our research lab, we decided to detect these compounds using paper electrodes. And also the biggest issue, as I said, it's heavy metals and uranium, right? Our groundwater is completely contaminated. So we also targeted to detect these 6 heavy metals: arsenic, lead, mercury, cadmium, copper, and chromium. And I'm going to show you the results. And as I said, we started with some simple concept, making paper electrodes. And this is our next lab, and my student Michaela Bigeshi is fabricating paper electrode. And we used a commercially available wax printer. And nowadays this printer is phased out. This printer is not available in the market. It got phased out, but still we bought these printers from local vendors, and we use this printer to create the wax barrier on chromatography paper. So we print this. Basically, we designed this using Microsoft Office. We create the wax barrier, we print it, and our students usually manually coat the conductive carbon ink, which is electrochemically active carbon ink, and we coat it, and we fabricate the paper electrodes. We deployed it in 3 electrochemical cells, and we did all this target analysis using this paper electrode. So this is a simple Wattman A chromatography paper. And I'm going to show you some nice videos made by my students. So it's all about paper electrode fabrication. And we got nice results for this heavy metals detection and biomolecules detection. We compared our paper electrode results for arsenic sensing with gold electrode. We got nice oxidation peak for arsenic oxidation, and you can see the calibration plot. So for increasing concentration of arsenic, the peak current is increasing, and we can calibrate, and we can draw the calibration plot. From there, we can calculate the linear range, detection limit, and sensitivity. And we also deployed paper electrode to detect dopamine, which is a neurotransmitter. You can see the nice electrochemical oxidation and reduction signals for dopamine in phosphate buffer solution. And this is the scanning electron microscopic image of carbon electrode printed on paper substrate. And these two are BPA and BPB detection. So you can see the electrochemical oxidation of BP compounds, and it is increasing with respect to the concentration. And this is the calibration for plot for BPA, and this is for BPB. So our electrode is capable of detecting arsenic, dopamine, ascorbic acid, and BP compounds. And also we use different electrochemical techniques like differential pulse voltammetry to detect BPS. So we also got nice electrochemical oxidation peak for BPS. And we are continuing the research to, this work is almost done. We are going to get it published soon. And the next one is LIG. I'm going to show that in next slide. But our work is highlighted by the previous NSF director in National Science Board meeting. And these are all my students. We also collaborate with Harvard University. We took this picture in Harvard, and this is our NEST lab. So with paper, we got some nice results, but how about the lifetime of paper electrode? It's not rigid, right? So we thought that we had some difficulties in handling those paper electrodes. So we started thinking about screen printing, lithography, and extrusion printing. And with our facility, with our infrastructure, we cannot accommodate all this, high-level printing research. So we thought that we should go for something else, and we decided to buy inkjet printer. We bought it, and we started the research. But we also thought something else. We can again think something simply to fabricate these electrodes. And we started with laser. And using lasers, you can burn any surface and you can generate graphene, right? So we thought that why don't we use laser, and literature, people already started publishing papers on this. So we decided to adopt this technology. And here we use Kapton film. So Kapton is a polyimide film. And this film was developed by DuPont, who developed the Nephron film. And it has an exceptional electrical insulation. And it is used in various industries, including aerospace and electronics. So it is used as an insulator. But we thought that why don't we use it for electrical conducting by burning the Kapton film using the laser. And that's how this research started. And using laser engraver, we can burn the Kapton film and we can generate the graphene surface, which is electrochemically conductive. And we optimized the laser engraving speed, laser speed, so that we can vary the seat resistivity. And from there, we can get a good electrode. And that's how we fabricated a LIG electrode. So this is our second product from NEST lab. So as of now, we are fabricating these electrodes in air environment, which has more resistivity, but we are moving in this direction, argon-based fabrication, so that we'll have more conductivity on our electrodes. And this laser engraving machine costed us $5,000. It's not a big money, and you can see our students fabricating this laser engraved graphene electrode in NEST lab. And I'm going to bring some videos. So it's a simple process. Once you optimize the laser power and the speed, and you can get the good conductive surface. And these are all fabricated electrodes, and we call it as LIG sensors. So you can cut it and you can deploy it as an electrochemical sensor. And these are all the conditions. We optimize the laser power and the running speed to get the best electrodes. And now we have a fully optimized condition to fabricate multiple electrodes at one time. So from manual fabrication to automation, we moved on LIG, and it's easy for our students. They like it because for paper, they have to coat the ink, right? But this one is super easy for them. And these are all the SEM images captured at NTU. And we got the same results as published from other people. And as an electrochemist, I always go with ferricyanide system first. So I asked my students to run this redox couple to test the capability of electrode. So our LIG has the capacity of oxidizing and reducing the ferricyanide system. And after this, we confirmed that our electrode is a good conductor. It can oxidize or reduce the substance. And we immediately deployed this electrode to detect dopamine. We used a differential pulse voltammetric technique to detect dopamine. And you can see the nice electrochemical oxidation peak. It is increasing. And we can measure the current. We can draw the calibration plot. And from there, we can calculate the reduction limit. And we deployed the same electrode for uric acid sensing and also ascorbic acid sensing. And it showed much better results compared to paper. And the ultimate target for us to detect these compounds in a mixture, because in electrochemical sensing, if you draw the blood, all these compounds are going to be in a mixture format. So we targeted to detect these compounds simultaneously and selectively. So our electrodes are capable of detecting this simultaneously, dopamine and ascorbic acid and uric acid. And still this research is ongoing, and we are also deploying these electrodes for other sensing such as heavy metals. So we also deployed these electrodes to detect cadmium, lead, and copper. You can see the electrochemical oxidation peak for cadmium, lead detection, and copper. And we varied the concentration, and our electrode is capable of detecting these compounds for various concentration, and which shows that we can deploy these electrodes in the field to detect those heavy metals in our groundwater, river water, or lake water. And my ultimate target is to develop uranium sensors, because we have uranium contamination, right? So I started with cadmium, lead, copper, moving towards core chromium, and uranium is our ultimate target. So we are working on this. So not only sensors, as I said, energy storage is my another area of interest. And we collaborate with Harvard University. And Justin Platero, he is my research staff, and Michael Melwood, he is in UNM now. I sent both of them to learn 3D printing technology in Harvard. So they learned how to fabricate 3D printed battery electrodes for flow battery application. And this technology is from Professor Jennifer Lewis' lab. She is expert in 3D printing. And still we are learning how to create these electrode inks and how to print this using the 3D printed electrode architectures. And this is going to cost us $400K to buy this entire setup. So still it's in the transfer process. We haven't completely transferred it. And we are targeting to deploy these electrodes for flow battery applications. And this is also in process. And what else we do at NTU? We also train our students to integrate their culture. And as I said, most of our students are Navajo students. So we also conducted dyeing and knitting research through our PREM project. And this is our chemistry lab. And you can see our chemistry lab technician, Melanie Herbert, is helping our students to do the characterization studies of Navajo dyes. So Navajo plants, they can extract Navajo dyes from those plant materials such as Navajo tea. We have various plant materials from those plant materials. Navajo elders extracted those dyes, and they dyed those and they weaved those Navajo rugs. So this is another outreach activities we do at NTU. And Crown Point to Harvard. And Robinson Tom, he is my first biology student. I also mentored biology students, and I started chemistry program in 2023. So he was with me for almost 4 years. He also worked with me in Army Research Laboratory in battery manufacturing. And he was completely trained at NIST Lab. Now he is a full-time grad student at Harvard. So sending students to Harvard is not an easy task. They collaborate with us, but still they won't accept students as like that. You have to train them, you have to mentor them. And he's also a US Army veteran. He served in Afghanistan, and he's a full-time grad student. He also won the NSF GRFP scholarship, and he is going to graduate soon. I hope he's going to come back to NTU as a faculty. And he's working, this is another image. He's working in NIST Lab, and he's completely trained electrochemist. He's doing something different now. He's focusing on microfluidics. I'm okay with that, but he's my first product. I'm proud to say that he's more successful in his research. And second student, Michael Melwood, he's also trained by me in electrochemistry research, and he did his postbac studies at Harvard, and now he is in UNM. So he want to come back. He don't want to stay in Boston, and he want to come back. So he joined as a grad student in Professor Gabriel Lopez group. He's there, and he is with his mentor, Aziz, I forgot his name. I'm sorry about that, but he's from Jennifer Lewis group. So this is the entire setup. It's going to cost almost $400K for us to establish this at NTU. So he learned this 3D printing technology at Harvard. And as I said, all of my students are undergrad students, and I also have some alumni. One is in Harvard, another one is in UNM, and also 2 other students. One is in UNM and another student in University of Idaho. This is my entire team. And I would like to thank these agencies for the great support. Without their support, it is not possible to establish these facilities. I would like to thank USD and IFA, NSF PRIMS, and DOT grants. And with all that, I want to teach another word, which is called ahihi. Thank you, and I'm happy to accept any questions.
We have some time for questions. Alana?
Yes.
Thank you so much for your talk. I'm just wondering, what is the limit of detection that you have right now? Could you show a little bit?
Yes, so that's a good question. As a sensor guy, we always target about linear range and detection limit. So my student still calculating the right number. He is doing this error analysis, and as of now, I think our linear range we can show our linear range for these compounds from 1 to 7 millimolar, but he's calculating. So that's why I haven't added those numbers here. So I know we have to get those detection limits, sensitivity, and he's writing the manuscript. So hopefully the next person in our publication, you can see those numbers.
Max.
I have a few questions. Let me know if I overstand. I love them. So first, I worked with a couple of groups who are really like Navajo Nation focused. I don't know if you know Dr. Naomi Lee or Dr. Janie Ingram. They're both focused on like cancer and environmental protection. But I think a big issue that both those groups have is outreach to the Navajo communities to like try and spread the message and everything like that. So how have you been doing that with like this, just the university, the programs that you're teaching? How do you get the word out there to have these people actually come to the school?
Okay, so that's a good question. So Navajo Nation is governed by chapter houses. We have 120 chapter houses, and Crown Point chapter house is nearby the main campus, and some of our students are from Crown Point, and we collaborate with 3 chapter houses: Crown Point chapter house, Besantee chapter house, and Little Water chapter house. So I ask my students to get their approval. So we go there, we give a hands-on demonstration there to encourage students to learn this research, and also we create this awareness inside the community. So if you approach those chapter houses, it's going to be easy for you to spread those messages within the reservation. Otherwise, it's going to be difficult. Approaching tribal community is not an easy task. Even for me, I'm a foreign faculty, but I'm half an Navajo now, almost 9 years with Navajo Technical University. I know my students, they can do it. So I ask my students to talk to their elders, and they get the approval. And that's how we promote our research and do the outreach activities. So we have 120 chapter houses. I know Flagstaff is also nearby Navajo Nation, right? So you guys may have some chapter house here, right? So if you approach them, you can do the outreach activities. And another thing I forgot to mention, we also started detecting cancer biomarkers using paper electrodes. So we got some nice signals for breast cancer. It's in the preliminary stage, so I don't want to show it here. So we are also focusing on that.
On that subject, the paper electrodes, I was wondering, I saw some reference to carbon, but are the working electrode, all the different 3 electrodes, are those all the same electrode material?
That's another good question. So ours is pseudo reference and pseudo counter. So still we can coat silver ink. That's possible, but I want to give something simple, simple for my students, so that they can just use the conductive carbon ink to fabricate these 3 electrodes. So all 3 are the same ink, but still we can keep a drop to mimic the silver chloride, which is possible. And counter, you can use the silver ink or other ink, but it's okay. Like, this is a pseudo reference. So still you can compare it with standard reference.
And then my last question is for the 3D printed sensors. I know that 3D printing metallics and everything is still basically in its infancy, but I know it's also really thin film. So what do you expect the longevity of these 3D printed sensors to be performing redox on the surface of?
For flow batteries?
Yeah, the 3D printed, yeah. For
flow batteries, I think this is a little bit complicated. As I say, like, still it's in the transfer process. We haven't completely understood. So that's why, still I'm a little bit hesitant. If I spend $400K on this, I'm really worried about the output. Paper electrodes you can deploy, LIs you can deploy, you can distribute to the community, but this one is a little bit tricky. So still we are investigating those things, but I'm not sure.
Thank you. We have a question online from Jolene.
Mhm.
Can you hear us, Sean? Can you?
Hello.
Yes.
Please can you hear me? Okay. Thank you so much for the presentation. That's such a good research you're doing over there. I think my question is about you mentioned that you want to do this research on a larger scale. So my question was about have you already tested the longevity of these electrodes, and then if you've done so, what are some of the techniques that were used, to check the structural change and chemical, let's say, change of the electrode? And also, if that have been done, what are the ways to improve it? Yeah.
Could you? I'm having a hard time to hear. Could
Uh,
you type your questions, please?
Okay.
While she's typing her question, we can take one from the audience. Philip?
Yes.
Thank you very much for talking, and I'm really impressed how you are giving back to your community. I have a similar question to this question about the paper printing and then the printing the detectors on the inkjet spreader. So over time, to like this degree, because you showed us some that can last, some sensors on the market that can last up to 365 days. So how long do your sensors last, and how can you reuse them? How often can you reuse them before like they give up?
That's another good question. So paper sensor is cheap, right? You can dispose it like single usage. But LIG, I think we test the reproducibility and reliability. It's for 1 week, so we have a good electrochemical signals even after 1 week. You have to store it properly. But all these are like low cost sensors, so you don't need to reuse it again. So my target is to fabricate low cost sensor which can be disposable. We can dispose it, right? So that is my target. So. But LIG, we have like 1 week lifetime. Yes.
So on the piggybacking off of the LIG lifetime, are there any durability concerns that you do with the paper sensors? Because the paper sensors, I could assume, could get damaged relatively easily while being used.
Mm-hmm.
Do you have any sort of concerns with that with the LIGs?
LIG, we don't have that kind of stability issues, but we found some different issue like we usually drop cast our target analytes to detect, and due to the hydrophobicity, the target analytes are leached out through the electrode surface. So those kind of issues we are facing. But compared to paper, LIG is much better. So you can use it multiple times, and it's reliable, and you can bend it. Even our paper electrodes, we can bend it, twist it, we'll get the same electrochemical signal. But if you immerse in water or like in phosphate buffer or anything, yeah, we have a wax barrier on backside, but still it's an issue. But compared to paper, LIG is better.
Thank you.
Thank you.
So the Jolene's questions
Yes.
now up there.
Okay, so long-term performance of the electrode being considered. If so, what techniques were used to determine the structural and chemical changes, and what is the best method to improve the lifetime? Okay, so 3 questions here. I think for long-term performance, I think I'll go with the LIG. But still, if you see those sensors, those pregnancy test kits and all other test kits disposable, it's still based on paper. So paper is best for disposable thing, and I'll go with LIG. And the techniques, we always go with CV first to study the electrochemical redox behavior. But if you think about commercializing those sensing, we always go with amperometric IT techniques. So we have 15 electrochemical techniques: CV, LSV, DPV, square wave anodic stripping voltammetry. We have almost 50 techniques, but for commercial sensing, we'll go with amperometric IT. I hope I answered your question.
Are there any other questions? Yeah.
What made you decide to go into teaching? Because like for 9 years you did like hardcore research, but now you're into teaching. What made you decide to go that route? Okay,
that sounds okay. So as I said, I think he introduced my background. I did my 2 postdoctoral research in R1 institutes. Okay, and I also worked as a scientist in Siemens Healthcare Diagnostics in Delaware for 3 months. I know what they did, and I really don't like. I made more money there compared to NTE. I was there until 2015, and I decided to quit. And I started looking for faculty positions, and Navajo Technical University hired me first. So that's how I started my career in Navajo Technical University, which is not R1, not R2, not R3. It's a tribal university, completely dedicated in teaching. So I have enough teaching load. I teach 4 courses per semester, including labs. Beyond that, I do all this research. This is my passion. So that's more. I still want to keep my research, tied up with my teaching. So that's how I started this, and I'm really excited to continue both. Even if you are in R1 institute, you have to teach 1 per 1, right? Per semester,
Yeah.
right? If you have grants, 101, and if you don't have grants, you have to teach 2 or 3. So yeah, it's really hard to manage, but in that way, if you teach course, you can attract those students to do the research. You can invite them to join your group, and it's based on the patient. Like some of them they like only teaching. I know our school has some faculty, they don't want to do research. They always dedicated in teaching. They just teach and they just leave. But my passion is to teach and do the research. And our group is small group, but still we have 2 Zoom meetings every week, every Tuesday and Friday. I have a group meeting with my students, and I do the work with them. I sit with them, I teach them, I train them in research. I don't have postdocs, I don't have grad students. I'm the postdoc, I'm the grad students for the rest.
I may have missed it, but what material do you print the LIGs onto, and then how does the cost compare to the paper electrodes?
So LIG, we just burn the polyimide film and we generate carbon surfaces. It's graphene. So LIG film compared to paper, it's expensive, little bit expensive, but still it's in cents. So if you see here, this is just burned surface, polyimide surface. It's a simply carbon graphene surface. You can also modify this graphene surface with suitable nanomaterials to modify these electrodes, and still it's going to be cheaper. But compared to paper, it's a little bit expensive, but it's going to be in cents only.
Thank you.
One more question, Dylan?
Yeah, so I was just curious about the handheld sensor that you can just simply connect to your cell phone.
Mhm.
So how does the accuracy compare to the accuracy of your handheld sensor compared to the clinical methods? Like, is it reliable enough that you don't have to go to lab for blood work anymore?
Yes. Handheld device, nowadays, like everything is miniaturized, right? Like 20 years back, we had a large sized UV spectroscopy, right? Now the size of UV spectroscopy is small, like tabletop, you can move it anywhere, right? Same like that, the bipotentiostat, it was larger before, but I think, it's reliable. You can compare those results with lab results. So this is from PalmSense. You can connect this to your cell phone, and this is what we are fabricating at Nest Lab. So the electrodes, the modified electrodes, and you can compare this results with the standard analytical lab techniques. Yes, it's pretty much comparable. I don't have those data to show, but you can compare the detection limit using paper electrode, and you can compare the same with the HPLC or GCMS, whatever we use in the analytical lab. For analytical lab, you have to draw the sample, you have to send it to the laboratory, or you have to visit the lab, right? And you have to wait for 3 days. But with electrochemical sensing, you can get the results immediately on your screen, on your mobile. So this is going to be, so I'm thinking that, like, so if you look at this glucose sensing, the continuous glucose monitoring, this is another good example. So you can patch this on your arm for 2 weeks, and this one says 365 days, and this is only for glucose now. Who knows, we will get one like a smartwatch, which we can wear continuously. We can monitor all kind of biomolecules like stress, cortisol sensing, like we have multiple biomarkers, right? So these sensors are reliable, and you can compare with the standard analytical chemistry lab testing.
All right, thank you.
Yeah, I just want to say real quick, one, it's fabulous. Thank you for that. And one thing, just that the students one of my students from me talked about this. One thing I'm just blown away by is again, I'm from the area, you know that from Gallup, and you know the Puerto River, we call it the Perky. So I used to, whenever it rained, I was playing in uranium water, which explains a lot about me. Yeah, like growing up there, I know exactly what that's like. But your ability to take, I mean, we're saying inkjet printers and these novel approaches. I feel like sometimes we get resources are great, but then they also can hamstring us because then we depend on just the most extravagant technology, and the innovation of what you're doing there, I think is just mind blowing. I think it's amazing what you're bringing to the community students. So I just want to say thank you for that. And yeah, just tremendous stuff.
Thank you. See, I know I bought the inkjet printer, but still I have to stick with Fujifilm to get the material.
Right. Yeah.
So that's why I told my students we should fabricate our electrodes by ourselves.
Right.
Using the materials available, whatever available. But still we can patent this technology. As I said, we are sensing cancer biomarker, breast cancer. So if we patent it and if we publish it, I think they can also start their own startup company. So my ultimate target is to train them to become entrepreneurs, to bring more workforce inside the reservation. Because all of my students, after their graduation, they have to leave the community. I really don't want them to leave the community, because if they leave the community, who is going to come back, to serve the community, right? So that's how this idea started, and it's going well. Hopefully we'll have publications soon and also patents. I'm waiting for that.
If you have any questions, we are having the lunch at 12:30, so make sure you come by, ask more questions there. But let's give one more applause.
That was fabulous. Sounds fun. Ryan, I want to introduce you to the group. There's yeah, I went to breakfast with one this morning, and one of the things we're talking about, because I have like this is Ryan Bahunin, and so when we're talking about quantum this morning, quantum sensing is an area that has some big, well, Sun's got us some ideas about, but I have some thoughts about too. We introduced